Everybody, it's Mrs. Harbin. Our last video notes for chapter 12. We're going to do a lot of math problems in this one, so try to pay attention so you get examples for each. Alright, so what should you read in the book? You definitely should make sure you've read section 17.9, okay? The pictures and examples can help you understand. So, alright, just get back to dissolving equations, because we're going to be talking about solubility. So here's the ionic compound. Here's what you have if it dissolves. Okay, so you got a calcium ion, which has a +2 charge, had a no periodic table. You got a chloride ion, but two of them, each of them has a negative charge. So when this dissolves, you get 3 particles per one dissolving. Okay, this is actually an equilibrium, because if it's saturated, all of this is constantly turning back into that, and vice versa, to keep these concentrations constant. Potassium fluoride dissolves into aqueous potassium ions and aqueous chloride ions. Okay, so you get 2 for 1 deal. What would the KSP be for them? Well, K means constant, and it's going to be an equilibrium constant. So what you would do for the first one, the KSP for the first one, would be equal to the concentration of calcium ions times the concentration of chloride ions squared. Okay, so that's the first one. The second one would be the KSP is the solubility product constant. Why didn't I put anything about underneath? Because those are solids. Okay, so you got potassium ions and you have chloride ions, no coefficients, so no squared. Okay, so you have to be able to write a dissolving equation and write a KSP for each dissolving equation. Solids don't go into the KSP because it's an equilibrium constant. Solids concentration doesn't change. What does this really mean? Well, if we just put this solid stuff into this flask, okay, it's all stuck together because it hasn't dissolved. But when it does dissolve, the ammonium dichromate solid will dissolve into 2 moles of ammonium ions that are aqueous and 1 mole of dichromate ions, which are also aqueous. So this is 1 mole of this makes 2 moles of that and 1 mole of that. So you get a lot of ions in solution, 3 times as many as you had solid particles. And it's an equilibrium. Okay, as some of it's dissolving, other is reprecipitating, unless it's an unsaturated solution, then it's all dissolved. Okay, so here we go with calcium chloride, and it gives you your KSP, which tells you pretty much to what extent it dissolves. What are the concentrations of the ions? So we'll start with this, even though I know you just wrote it down. It's in equilibrium with its ions, which are aqueous, and its chloride ions, which are aqueous. Okay, and then the KSP is equal to the calcium ion concentration times the chloride ion concentration, and that has to be squared because the coefficient's 2. Okay, so now if we look at it and say, well, if some of this dissolves, I'm going to get X amount of that and 2X amount of that, because you get twice as much. Okay, well, if we want to know what the concentrations of the ions are, we have to take the 1.57 times 10 to the negative 8th, which is the KSP, plug in X for calcium, 2X for the chloride ions, and that's squared. So we're just plugging X's into there, and now we're solving for X. So we have X times 4X squared is 4X cubed is a 1.57 times 10 to the negative 8th. Right? And then we'll just divide both sides by 4, and we get 3.93 times 10 to the negative 9th. You could plug it in your calculator to make sure. That's X cubed. Now we can take the cube root of each side, cubed root. So X is going to be equal to 1.58 times 10 to the negative 3rd. Now, X was the concentration of calcium. So that's going to equal your calcium ion concentration. But the chloride ion concentration is 2 times that. So the chloride ion concentration is going to be equal to 2X, so it's going to be 3.16 times 10 to the negative 3rd molar. Okay, so how do you figure out that concentration of ions in a solution when you're talking about dissolving? You use the KSP, you figure out how many ions you're going to get, you plug it into the KSP itself. Okay, It's one KSP problem. There's another type of KSP problem, magnesium hydroxide. So let's start by writing this out. It has a solubility, so it tells us solubility in grams per milliliter. And then we need to write a balanced equation representing the magnesium hydroxide equilibrium. So magnesium is a +2 charge. How do I know? Periodic table. 2 hydroxide ions. How do I know? Hydroxide's a -1, and there's 2 of them in there. Okay, so we did that. Write an equilibrium expression. So I'll put it down here because I'm going to write under it. The KSP is going to equal to the concentration of magnesium ions, because they're aqueous, times the concentration of hydroxide ions, also aqueous, squared because the coefficient's 2. Now we need to figure out the KSP. We don't know this time, but we do know this. This is in grams per milliliter. So instead of just plugging it in, we have to figure out moles per liter because of these brackets mean molarity. So I'm going to start with the 9.24 times 10 to the -4th grams for every 100 milliliters, because that's the maximum that can dissolve. That's the solubility. It tells you how to make a saturated solution. But we want to plug in moles per liter in there. So I would say, well, that means that we need, let's see, 58.32. Where'd I get that? Grams from the periodic table. That's magnesium hydroxide for every 1 mole. So now it's going to change to moles per 100 milliliters. But we want that to be liters. So I'm going to say, well, milliliters. So milliliter, there's 1,000 milliliters for every 1 liter. So when I multiply that out, I get 0.000158 moles for every liter. So that's molarity. Okay, what is that the molarity of, though? Well, this is the solubility of magnesium hydroxide. So if all of the magnesium hydroxide dissolves, because that's what solubility means, that you're making a saturated solution, then I'm going to get X amount of magnesium and 2X amount of hydroxide. So if all of this dissolves, and that goes from X amount minus all of it, I'll get X of that and 2X of that. So that's what I have to plug into the KSP. So the magnesium is 0.000158, and the hydroxide is 2 times 0.000158, but we also have to square that to get KSP. So you plug that into the calculator, and just to you see where I'm coming from here, 0.00158 times 0.000316, because that's 2 times that, and then you square that. When you do all that math, you get that the KSP for this magnesium hydroxide at this temperature is 1.58 times 10 to the -11, okay? And you can see that this is a small number, which means magnesium hydroxide does not dissolve very much because the K is pretty small, okay? So we used to say that things were soluble or insoluble. Now we can even get closer to they dissolve a tiny amount or more or less. So that's what the KSP can help us decide. Okay, now we're doing a different kind of problem. What is molar solubility? So that means how much can dissolve by mole per liter of silver chromate. Here's the KSP for it. So we want to know how many moles per liter of silver chromate can dissolve. All right, so let's start off with the dissolving equation. All right, so silver chromate as a solid is in equilibrium with the silver ions, 2 of them, and 1 chromate ion. All right, and that's all aqueous. All right, we know the KSP is, so we know it's going to be at equilibrium because the KSP tells us that. And so then we can say, well, we'll get 2X of that and X of that anytime one of those dissolves. Okay. So we could say 1 times 1.0 times 10 to the -12th is the KSP. Let's write out what the KSP equals. Equals silver concentration squared, because there's a coefficient of 2, times the chromate ion concentration. All right. So this is going to be 2X squared times the chromate ion concentration. So again, we get 4X cubed, divide both sides by 4, and we have 2.5 times 10 to the -13th is equal to X cubed. Take the cube root of both sides, and we get X is going to be equal to 6.3 times 10 to the negative fifth molar. But we haven't decided what this means yet. Well, X represents the chromate ion concentration. All right. X also represents the silver ion content, silver chromate, solid, because if you look over here, there's a coefficient of 1, and over here is a coefficient of 1. So this also describes the solubility of silver chromate. So the solubility of silver chromate is 6.3 times 10 to the negative fifth moles per liter. Okay, so that's how much can dissolve to make a saturated solution, because that's what solubility means. The maximum amount that dissolves to make a saturated solution. Okay, next problem. Whew, this is crazy. What is the solubility of copper 2 hydroxide in grams per liter? Okay, so in this one we wanted the solubility in moles per liter. This one we want solubility in grams per liter. So it's just going to be one more step more. But we need to make sure that we can write a chemical formula. This is solid. This is a +2 copper charge. It's a -1. So we need 2. All right, we're going to get copper ions. Woohoo, copper ions. And we're going to get 2 hydroxide ions anytime that dissolves. Okay, now we have that. We have KSP. KSP equals the concentration of copper ion times the concentration of hydroxide ion to the power of 2 is the coefficient of 2. Okay, we should, if this is dissolved, we're going to get X amount of copper, but twice as much hydroxide, because there's 2 hydroxides per formula unit. So let's see what happens there. Okay. I did this one. Oh, okay. So here we go. I'm going to start plugging this in. 2.2 times 10 to the negative 20th, given in the problem, is equal to X for the copper concentration, 2X squared. Again, 4X to the third. Pattern, maybe. All right. Divided by 4, divided by 4. And so we're at 5.5 times 10 to the negative 21st is equal to X cubed. Cube root both sides. And we get 1.8 times 10 to the negative 7th. And that's equal to X. But what is this? Well, these were all, these are concentrations in here. So this is molarity. So that's moles per liter. So then we need to take the 1.8 times 10 to the negative 7th moles for every 1 liter. And we just need to change those moles into grams so that we get grams per liter. So, what are we talking about? Copper hydroxide, copper 2 hydroxide. So then 1 mole of the copper 2 hydroxide is equal to 97.57 grams. Where'd I get that? Periodic table, you betcha. All right, so that mole stuff is helping us along here. Moles of copper hydroxide cancel out, and we're going to get 1.8 times 10 to the negative 7th grams per liter. So that's the most copper 2 hydroxide that we can get to dissolve at the certain temperature. That's its solubility, grams per liter. All right, next problem. All right, this is taking us back a little bit. Q versus K. Q and K are found the same way. It's products over reactants, but Q is anytime, K is at equilibrium. For KSP, it's equilibrium constant, solubility, product constant, solubility, product constant. It is an equilibrium, but it's an equilibrium for dissolving. Okay, so if Q is greater than KSP, then there's a lot of ions there. So they will make a precipitate. They'll find each other, and the concentration of ions will go down. So the solution must be supersaturated, and that means the ions will find each other and make a solid. Okay, and this is for KSP. If the Q is less than the KSP, that means there's not enough ions around to make a precipitate, meaning it's unsaturated. Okay, there's not enough ions around. If Q is equal to K, it's saturated, no precipitate. This is tough to get a saturated solution because it's just that exact point where you can't add any more or else it'll precipitate out. Okay, so will a solution of 40 milliliters of 2 molar, 2 times 10 to the negative third molar of silver nitrate and 45 milliliters of 1.5 times 10 to the negative second molar of potassium chromate form a precipitate? Oops, form a precipitate, question mark. So what's going on here? Well, we have silver nitrate, and this as a solution, is reacting with potassium chromate, and that's also aqueous. All right, it's a double replacement reaction. We're going to get Ag2CrO4 and KNO3, and then we're going to need a coefficient there and a coefficient there. So this is really what's happening. Now one of these two is going to be a precipitate. So we look at our solubility rules and we find out that silver chromate should be precipitate. So that takes us back a little bit. So what's the real reaction going on here? What's the net ionic equation? Well, the silver ions, are they going to find the chromate ions to make this solid? But when we're doing dissolving, we do it backwards. So we say K, oh, sorry, not K. We're saying silver chromate, solid. We're going to try to see if it's going to precipitate. So we're going to make 2 silver ions, and that'll be aqueous, in equilibrium with the chromate ion, and that's also aqueous. So here's the dissolving equation for this one. Okay, and now we'll get this problem out here. So we have to figure out the concentration of this and this to see if it's bigger or smaller, then unplug it into the KSP. Okay, so we have Ag plus squared times the chromate ion concentration. Alright, so we have to plug in the concentration of that and that to see if it's bigger or smaller than the KSP. So we really want to find a Q. Alright, so that's the KSP, but we don't know if we're there yet, so we're going to call it a Q. Alright, so how do we figure out the silver ion concentration? Well, we have this solution and that concentration. Oh, we have an M1 and a V1, and this is a V2. Okay, so we have M1, V1. So for silver ions, the concentration of silver ions, M1, V1 equals M2, V2. And we have to find out the molarity of the silver ions after we mix those together. So the silver ion concentration is going to be M2. M2 is going to be M1, V1 over V2. So what's the initial concentration of silver ions? Well, we get 1 for every silver nitrate. So 2.0 times 10 to the negative third molar times the volume originally was 0.040 liters. All right, yeah, there's another 0 there. Divided by the final volume, which is 85, but 0.085 liters because I changed it to liters. So the concentration of silver ions in the solution is going to be equal to this, which comes out to be 8.21 times 10 to the negative third molar. Okay, not done yet because we only have this number to plug in there. So let's figure out the concentration of chromate ions. Where are the chromate ions coming from? Well, their concentration is going to be equal to the M1, which was the 1.55 times 10 to the negative second molar, times the original volume, which is 0.045 liters, okay, divided by the total volume, which is 0.085 liters. Okay, so those cancel, and we found out that the concentration of chromate ions in this solution, after we mix those two solutions together, is oh, I made something up. 8.21 times 10 to the negative third. You're like, but Mrs. Harbin, you just wrote that down for this one. Actually, I put the wrong answer in there. When you multiply 2 times 0.04 divided by 0.08, you get 9.41 times 10. Oh, come back. Times 10 to the negative 4. Okay, so what do we do now? Well, now we got to plug it into the Q to see where we're at. So Q is going to be equal to the silver ion concentration, 9.41 times 10 to the negative 4. Don't forget, we have to square it, okay, times the chromate ion concentration, 8.21 times 10 to the negative third. You don't have to square that because there's no coefficient. And find out Q is equal to 7.27 times 10 to the negative 7th. Alright, so KSP is 1 times 10 to the negative 12th. Q is 7.27. Q is greater than KSP. So what does that mean? It means right now, remember it's products over reactants, is greater than the products over reactants, which is KEQ. Okay, this is our K, this is our Q. So what do we have to make more of? Well, we have to get rid of products to make this number smaller. So that means to get rid of products, we have to get rid of these ions. So yes, a precipitate forms. Okay, it's a lot of work. We'll do some more. Okay, common eye effect. So if you have these solutions and all of a sudden, if you have silver nitrate, do you think it's going to be more or less soluble in plain water or silver acetate solution? Well, plain water has no ions in it. Silver acetate already has some silver plus ions. So if you put silver nitrate into a solution that already has silver, then it's going to be less soluble because less silver can go in. Okay, is potassium chloride more soluble in a solution of potassium nitrate or sodium chloride or ammonium fluoride? All right, what's common? Potassium chloride will be less soluble in potassium nitrate because there's already potassium ions. In sodium chloride, it'll be less soluble because there's already chloride ions. Ammonium fluoride is no effect, so it'll be just its regular solubility. Okay. So no effect. The ammonium fluoride, there's nothing common in ammonium fluoride. So if you have a solution of ammonium fluoride and potassium chloride, you're not affecting the solubility of this because there's no common ions. Okay, how does that look here? Well, okay, so here's a saturated solution of silver ions and chloride ions. If I add more hydrogen chloride, I'm actually adding more chloride ions. So if I add more chloride ions, the silver chloride will start to precipitate out because you're pushing the silver ions into being solid because you're adding more chloride. Okay. All right, a couple more problems just to make sure we're on the right track here. So, all right, we have this reaction. Let's write a K for it. Products N2O5, and that's going to be the second power over reactants NO to the fourth, O2 to the third power. Okay, they give us at equilibrium, here is the NO, so let's plug that in. NO is 2, that's going to be to the fourth power. N2O5 is 8, so we have 8 molar up there, that's squared. And O2 is 3 molar, okay, and that's going to be cubed. If we plug all of that in, we get 0.148, and that is 0.15. So we found out K is 0.148, and to sig figs it's 0.15. Okay, so that takes us back a little. Look, it says at equilibrium, so you can plug all of these in right into the K, and they're telling you it's at equilibrium, so that's the K. Okay, here's another one. All right, and I think this might be our last one. Whew. All right, here's a dissociation equation. All right, if the initial concentration is 1.5 molar, so we have, I'm just doing an ice table. Initial, we have 1.50 molar. Calculate the equilibrium concentrations of all species. So the H plus is going to be, we'll say 0 and 0. So this is H2SO3. This is H plus, and this is HSO3 minus. Okay. The change is going to be losing some of that. And when you lose some of that, you're going to gain some of that and gain some of that. At equilibrium, you're going to have 1.50 minus the amount that dissociated. And you're going to have X of that and X of that. So our K is going to be products, H plus, and HSO3 minus, no coefficients, over reactants, H2SO3, and that's aqueous, so it has to be in there. Look, aqueous. Okay, so then we plug in our H is X, our HSO3 is X, and at the bottom we have 1.50 minus X. So we have X squared over 1.50 minus X is equal to 1.2 times 10 to the negative 2, because that's our K. All right, what do we do next? Well, we have to solve for X so we can figure out the concentrations. And solving for X means that, this should be X squared because it's Texas. All right, so then we want to do X squared is equal to 1.2 times 10 to the negative second times 1.5 minus X. X squared is 0.018 minus 0.012x. Alright, so 0 equals 0.018 minus 0.012x minus x squared. Okay, well, you plug this all in, and you have to use quadratic this time because we can't take the square root of both sides. So plug that into the quadratic formula. Minus b plus or minus square root of b squared minus 4ac over 2A, and you get X equals 0.128 molar. But what does that mean? Well, that means that at equilibrium, the hydrogen concentration is X, is going to be equal to the HSO3 concentration, negative, which is going to be equal to 0.128 molar. And then the concentration of H2SO3 is going to be equal to 1.5 minus 0.128 equals 1.37 molar. Okay, so now you have another example problem of how to use a quadratic. Whew, that was crazy, but make sure you can do ice diagrams, all right? And make sure ice for KSP helps us find the X, which is the solubility, okay? Coefficients are important. Common ion reduces the ability to dissolve, okay? Read the book, please. Use the pictures to help you, and we'll work in class to make sure we understand all these, all right? Oh, can you feel?